the payoff side is labeled here in a confusing way so that you don't see 1. The game model is such that the total utility available is 1 when the players cooperate in a perfect manner. Now, the structure of the model will change the mathematical outcome. If E3 or epsilon 3 is not 0, it isn't where we calculate it. We just can look at the limiting form of it. Then demands are not perfectly sharp. There's a certain fuzziness. And so under these conditions, the players do not operate on the highest level of efficiency. But this was actually calculated that this is there are other numbers that are called B1, B2, B3. These are coalition strength descriptions in a 3-person game model. It's a simple model which really is derived from the idea of certain values of the coalitions. B3 is the value of the coalition of player 1 and player 2. If they simply get together without player 3, they can get a payoff of 0.2 in this case, for this calculation. That's 1/5. And, but also any 2 of the players can get a payoff agreeing separately of 1/5. But all 3, it's normalized. If all 3 cooperate, they get a payoff of 1. So the challenge, the mathematical challenge was, if the 2-player coalition strengths are different in this model, which might not be, it's not entirely like von Neumann and Morgenstern coalition values, because there is a technical point that the utility is not always perfectly transferable. But that is a little complication. Now, this chart was actually worked out in 2002. These points have a little blue color, and the first project assistant helped with developing a series of calculations there. Now, what happens is that when this E3 or epsilon 3 is quite small in a perfectly symmetric game situation, then the players get more than 0.9 fraction of the payoff that's available. Of course, it gets all of it as this goes to 1. But if this number is as large as 0.2, then the fraction they get is about half. So about half of the resources are wasted if their demanding process is a little rough, is not so sharp. I will not have time to cover everything. I'm prepared for that. Now, Pareto graphic. Now, a second project assistant worked out another case a little later on. And in this case, we had these B numbers that describe coalition strengths, what 2 players could get privately as differently. The only coalition was called coalition 3, which is of player 1 and player 2. The naming is cyclical. If they agree together, they can get 2/3 of all the payoff. So they're in a strong position. And it was possible to compute solutions here. And these are other numbers. These E4 and E5 I haven't described yet, but they're small. They're numbers that should be small, and they would go. We want the limit as they would go to 0, and they described some of the joining together, the process of joining together of the coalition members, and the process, the rules of election. So in this case, it turns out that you could see that the Pareto efficiency here, that's the comparison of the realized payoff with the possible payoff ideal in some ideal sense, it goes towards 1 as this E3 is very small. But if E3 is as large as 1/10, in this example, results are only in the 70% some percent level. This is normalized differently. Now, so I had to study I studied first the basic idea, well, in the case of 2 players, this mathematical stuff, and it worked out. And I talked about that when I was in Catania, and I was also by coincidence when I was in the meeting in Ischia. This was years back. Now here's a discussion about 2 players. You see there, I didn't really say what the election process was. How did this cooperation occur? Well, the way it would be with 2 players, either player would be able to accept the other. But this is like well, it's like being most cooperative in a prisoner's dilemma situation. Now, the other one then accepted, this is as if one player had first refused to confess to the police, and the other prisoner could somehow know that and decide whether what he should do. But the situation is going to be repeated in time, however. It makes it not so simple for a prisoner. So one player accepts the other player, and then in 2 players, then the other player is able to select a point on the boundary of the accessible area of cooperation. That's called the Pareto boundary, and he can accept it more or less favorable for himself or more or less favorable for the other, because typically this is a curve that has utilities being shifted from one player to the other player. And so that's how I originally made a mistake. I had the choice that if each player voted to accept the other player at the same time, that these 2 acceptances would be thrown out, and there would have to be another election, if there could be another election. But there would only be a finite probability that there would be, it wouldn't be certain that the players would be given another election, because they would be forced to try to be more practical and allow the process to complete. But later on, the final convention was, and it was found to work very well, if each player votes to accept the other, or generally it also goes for 3, then that a random process is introduced, and it takes one of those acceptances and makes that the effective one, so that one player accepts the other player. So this is the concept of demand, and this is still player. This is what I discussed before, but now we directly generalize from that to 3 players. Uh-oh.